Hi, I'm Vanessa, and in this talk I will give you some insights into our paper ShaRPy, Shape Reconstruction and Hand Pose Estimation from RGB-D with Uncertainty. So what is the application of our approach? Musculoskeletal diseases such as rheumatoid arthritis are hard to detect in early stages, as the state of the disease is not as clearly visible as in the image here. However, when we took a look at motions, we did observe that the patients show a high variance in their movements compared to healthy subjects. So the question arises, can we study the disease using motion? And currently we are recording a lot of different motion sequences in which we test the hand function of patients with and without hand-object interaction. So if we have, for example, a video like this, it would be desirable to analyze these motions in an objective manner. What we would like to have is a perfect digital twin of a hand skeleton in order to analyze the hand function through the joints. However, as we applied current state-of-the-art approaches for key point detection, we had to face a few challenges. First, key point-based approaches oftentimes speculate the positions of fingers even if they are not present in the data. And since we are interested in the truly observed motions, this is something we do not want. Second, it is hard to speculate a skeleton at its correct position if all you see is the outer surface of the hand. And last, it is really hard to determine whether we can trust the predictions since fingers might be mislabeled and this could bias our studies. So, to tackle all of these issues, we proposed ShaRPy. ShaRPy can estimate the pose and the shape of the observed hand, and it is the first approach that actually detects uncertain regions, so we can discard them in our hand function experiments. But how does it work? ShaRPy takes as an input a frame of an RGB-D sequence, for example captured from a depth camera, and outputs the pose, the shape, and the uncertainty of a parametric digital hand model. The pipeline consists of 3 steps: a neural hand detector, a pose and shape optimizer, and an uncertainty estimator. ShaRPy makes use of temporal data and reuses the observations of previous frames in the next step. So let's take a look at each of those stages in more detail. As already mentioned, our input is an RGB-D frame. So for more proper visualization, let's put this into 3D. In the first stage, a neural hand detector predicts for each point on the observed hand a feature coordinate in a novel canonical space which we introduced in our paper. With these canonical coordinates, we can establish correspondence pairs between the digital hand and the observations. The pairs are visualized as lines here. Based on those pairs, our optimizer computes the optimal pose and shape of a parametric digital hand model. But what if we have an image that is not so easy to predict as this one? So let's take this image for example. In general, our network has never seen clinical recordings like that, and apparently this partial view of the hand seems to be difficult. Hence, the canonical coordinates of the prediction are quite inconsistent. So we have to figure out which of them will lead to uncertain hand poses. The inconsistencies will become even more visible if we utilize the anatomic structure of our canonical space and convert the coordinates directly into a segmentation map. If we now try to estimate the pose and the shape of the hand, it is impossible to respect all the optimization constraints. So many areas of the digital hand either have no correspondences at all or are left with a high residual during the optimization. We cluster these findings per segmentation area, threshold them, and visualize the uncertain results in red for error-prone segments and in gray for unobserved segments. In the end, we can use the estimated uncertainty per segment in order to discard unreliable poses. We test our approach on patients and compare the results with the key point detector OpenPose, which has the challenges that I mentioned in the beginning. We also test our approach on challenging scenes in state-of-the-art datasets in combination with hand-object interaction. As it can be seen, ShaRPy produces smooth temporal results, estimates not only a skeleton but also a personalized hand shape, and visualizes the uncertainty on top of it. It's a very useful tool to be employed in hand function tests, and we hope that many other people will use it to study and monitor disease activities. Thank you.